Hello, this will be a demonstration of Proposition 21 from Book 3 of Euclid's Elements, which states that in a circle, the angles in the same segment are equal to one another. What we are given is the circle ABCD, so, and we have within it the segment BAED, so that would look something like this. So we have the segment here, BAED. This whole arc right here contains the segment like that. And in this segment, we have the angle BAD and the angle BED. And what we have to prove is that the angle BAD is equal to the angle BED. Now, this segment BAED can be one of three things. It can either be greater than a semicircle, it can be equal to a semicircle, in which case it would simply be a semicircle, or it can be less than a semicircle. Euclid's original proposition only actually deals with the case where it's greater than a semicircle. So I've added the extra little bits for if the segment is either a semicircle or is less than a semicircle. So let's begin with Euclid's original case, where the segment BAED is larger than a semicircle. And if it is, we take the point F as our center, which I'll say is around there. And then we join the straight lines. This is going to be a little hard. BF and FD like so. Now we know from the previous proposition that this angle BFD, being an angle at the center and standing on the same arc as BAD, BFD must be double the angle BAD. This is again proposition 320. Because of the same proposition, we know that the angle BFD must be double the angle BED, because they're on the same arc, BD like so. And C's down there, I forgot. And so BFD is equal to double the angle BAD and double the angle BED, which means that double the angle BAD and double the angle BED are equal to each other, and doubles of, oh, that's my bad. No, if doubles are equal, or if things are equal, then their halves are also equal. And so if double BAD is equal to double BED, which it is, we know that the angle BAD must be equal to the angle BED all on its own, the property of magnitudes. And that's where the original proposition ends. It only deals with this case where the segment BAED is greater than a semicircle. But there are two other cases, and the proposition is a little bit different in those cases. So let's take the case where the segment BAED simply is a semicircle. So this will look something like that. So we have BAED, and we're going to deal with the case for this segment BAED, so that whole thing is a semicircle. And if it is, we shall take the point F as the center. Center will be around there. We shall join the straight line AF. We shall carry this straight line AF to point C like so. We can take the center obviously by 3,1. We can join a straight line with postulate 1, and we can produce that straight line continuously in a straight line by postulate 2. And we shall finish our construction by joining the straight line EC, again by postulate 1. Now if we look at this circle right here, we actually have multiple segments that are greater than a semicircle. So if we take this segment right here, BAED, so that whole segment right there, it's greater than a semicircle. And we've just shown that the angles in a segment that is greater than a semicircle are equal to one another. And so when we're looking at the segment BAEC, we have two angles in it, namely BAC and BEC, and they're both in the same segment that is greater than a semicircle. And so we know that the angle BAC must be equal to the angle BEC. Similarly, if we look at the segment CAED, so that whole segment right there, we have two angles within it, CAD and CED, and both being in the same segment that is greater than a semicircle, we know that they must be equal. We have just shown that. And so we can say that the angle CAD is equal to the angle CED. And if we add these two together, Namely, if we add the angle BAC plus the angle CAD, it must be equal to the angle BEC plus the angle ECD, or CED. That's common notion too, adding equals to equals, the sums will be equal. And the sums in this case are simply the angle BAD and BED, right? So we have the angle BAD and it's cut into the angles BAC and CAD. And we have the angle BED, which is cut into BEC and CED. And so the sums of adding equals to equals, the sums will be equal. We know that the angle BAD must be equal to the angle BED. And that, now we're done with the case where the segment BAED is equal to a semicircle, simply is a semicircle. In the final case where the segment BAED is less than a semicircle, this would look something like that. BD, AE, join, like so. So this segment BAED is less than a semicircle. And we shall carry out the proof actually exactly in the same way as we did the other case. We shall begin by taking the center, point F, like so. We shall join the straight line AF and produce it all the way down to C. We shall join the straight line EC. We can do this by Prop 3.1 to find the center of a given circle, postulate 1 to join any 2 points in a straight line, postulate 2 to produce a finite straight line continuously in a straight line, and finally another use of postulate 1. Now again, if we look at this segment BAEC, so that's that whole segment right there, it's greater than a semicircle, and so we can say that the angle BAC is equal to the angle BEC. For the same reason, in the segment CAED, so that's that whole segment right there, the angle CAD is equal to the angle CED, again because we just proved that in a segment that is greater than a semicircle, the angles in it will be equal. And so the angle BAC is equal to the angle BEC. And we can also see that the angle CAD is equal to the angle CED. And if we add these angles to each other, their sums will be equal. So the angle BAC plus the angle CAD, that is the angle BAD, is equal to the angle BEC plus the angle CED, that is the angle BED. And so again, we arrive at the fact that the angle BED must be equal to the angle the angle BAD must be equal to the angle BED. And we have proven in all three cases, whether the segment be greater than a semicircle, whether it be a semicircle, or if it be less than a semicircle, the angles in it will always be equal. And so we've shown sufficiently that in a circle, the angles in any segment, the angles in the same segment, if the segment be any segment, the angles in the same segment will be equal to one another. And this being what we set out to prove, we are done with the proposition, therefore, etc. QED. I hope you guys liked my little additional proof here for the cases which Euclid does not include. I don't consider that a shortcoming of Euclid. I mean, these proofs are awfully simple, but I do think it is necessary to spell them out in full. So that being all I have to say about this proposition, I shall move on simply to 322.